Welcome to the International Industrial Chemistry Conference 2021, hosted by the University. I would like to thank the organizers for creating a platform to solve industrial chemistry problems and see the future directions in this field. Thank you for the invitation. Today I'll share some of our success stories in reducing the analysis time from hours to a few seconds. And secondly, we will also briefly touch upon the use of supercritical carbon dioxide as an alternative to toxic solvents. Fundamental research and development is a slow and a very expensive process. For example, in order to develop a new drug, researchers screen about 5,000 potentially interesting molecules. And out of those 5,000 interesting molecules, only 5 are promising for further research. Finally, it takes about 12 years on average for a brand new drug candidate or a molecule to reach the patient. And in the end, a pharmaceutical company or research organization has spent about $2.5 billion. As stated previously, investigating 5,000 molecules in the discovery process is not an easy task. Often researchers have to wait for a long time to get the analytical results back after experimentation before they can do statistical analysis or interpret their data. Let's do a quick arithmetic. Suppose you are doing screening of drugs in well plates as is done in discovery process quite frequently. And if your analytical method takes around 30 minutes, which is a typical time frame of instrumental techniques, you will have to wait for 2 days in order to analyze 96 samples. If your high throughput experimentation grows to 1500 samples, you literally have to wait for a month and you cannot do anything without getting the numbers back. Now the same 1500 samples and experiments can be analyzed in 26 hours if our analytical method could be carried out at under a minute or under a second that's our goal. So we have two options. Either we use electrochemical or optical sensor, which are really fast. They take less than a second, sometimes a minute. But the price of speed is that you are limited to a single component. Recall your blood glucose sensor. It only tells you your glucose level in the blood and does not know what else is present in your blood. Alternatively, we use separation techniques which are slow, but they can analyze multi-component systems. Chromatography can easily handle the whole blood components and analyze what is present. As for the sake of comparison, direct blood glucose measurement by liquid chromatography or mass spectrometry takes about 470 seconds, and a blood glucose sensor takes about 15 seconds. Here is an environmental case of ion analysis. One can buy ion selective electrodes, and for each ion there is a different electrode. And the response time is typically less than 10 to 50 seconds. For the sake of comparison, let's take the example of chromatography. It can easily analyze 44 ions in 40 minutes or 53 seconds per ion. So the focus of my talk is the column section as shown here on the left. How to miniaturize it, how to miniaturize the column, and how to develop better silica surface chemistry for high-speed analysis so that we don't have to wait for a minute or 40 minutes. Rather, we complete our analysis in less than a second. In 2017, drug discovery scientists from Merck, USA, wrote an interesting article on high throughput analysis. So they said that while 5 to 30 minutes for the chromatographic analysis in antipurity are still used to support research investigations in many synthetic and pharmaceutical research laboratories, in many cases these assays can be easily replaced by much faster methods enabling enantiomeric excess analysis of over 1,000 samples in an 8-hour workday. So you can immediately see the scale of operation where the industry is going, where the goal is to analyze 1,000 samples in an 8-hour workday. How can analytical chemists help to speed up things? We have to go back to the theory then, and then learn from the resolution equation, which has 3 factors. The number of theoretical plates, which is n, and you can see in the graph that n has a square root dependence, and alpha value, which is the relative retention factor or the selectivity, it is dependent on the surface chemistry and the solvent environment that is provided to the analyte. And this is actually the most important factor, and you can see it's almost linear for resolution in the graph on the left. And the least important factor is the retention factor, which is K, and it does not matter much, and it's a thermodynamic property as such. So I'm going to focus on the resolution equation, the first two factors, and especially the theoretical plates and how to optimize silica surface chemistry for high-speed separations. Coming to the theoretical plates part of the resolution equation. Here we show different morphologies which can allow us to do ultra-fast liquid chromatography. First is the classical version, which everyone is familiar with, that use spherical, fully porous particles. But they're low efficiency and they exert high back pressure, so they have very high resistance. And that's why you need very high pressure pumps to push liquid through those columns. But we have moved on to core shell silica, which consists of a solid core and there is an outer layer of porous particles. And this is the latest technology to obtain very high efficiency peaks or peaks which have very narrow widths in chromatography. Another development is in the last 2 years or 3 years is the use of knot columns. They are called as narrow open tubular columns and they are used in liquid chromatography. And some people can recall that GC columns have open tubular columns as well, but these columns which are used in LC or which have been proposed in LC, they're extremely narrow. Their micron dimensions, they have micron dimensions. Lastly, the silica monolith is a porous structure, just like a sponge made of silica. And it has low efficiency, but it does have very high permeability, which means that it exerts very low back pressure. And with the low permeability, you can easily use high flow rates with that. And high flow rates means faster separations under some cases. The next question is how to optimize the silica surface chemistry so that the value of alpha in the resolution equation is large. Chiral analysis is legally required in the US since 1992, and 80% of the approved drugs, new drugs which were discovered in 2000 were chiral, and 70% of them were single enantiomers. So chiral analysis is a must. So bare silica itself is useless. It cannot recognize chiral molecules. It just provides efficiency. It only provides narrow peak widths. But we need to modify the surface so that it can retain the molecules of interest. We can bind different type of molecules. So one of the strategies we came up with was to bind natural products to the silica surface. And vancomycin, teicoplanin A glycon, they are all chiral molecules and they can be bonded to the silica surface. Similarly, you have cyclodextrin, which is a sugar molecule. This is also chiral. And there is another famous quinine molecule that can also be bonded to silica. How do we bind those large molecules on the silica surface? They can easily bond it by using something called as the linkers, using silane chemistry. So silane chemistry allows you to bind one end of the chain to the silica particle and the other end of the chain is bonded to the big macrocycle or cyclodextrin or whatever molecule you want to bind there. So now you have a completely bonded surface and now you can use those particles for performing chromatographic experiments and using chiral analysis. Now that we have optimized silica particles using core shell technology and we have modified its surface, it's time to choose the best column geometry now. So you can see conventionally we have been using 25 centimeter long columns packed with 5 micron silica fully porous particles. So this is in the industry for more than 30 years and the separation is really slow. You have to wait for an hour or so on. But with time you can see the miniaturization is happening and we are going towards shorter and shorter columns. So this talk is going to focus on the columns which have been packed with scortial particles, and their dimension is around 0.5 to 1 centimeter length. Now there is a challenge here, that once you have the silica particles and you have those small columns, stainless steel columns, how do you pack those particles? How do you fill those up? It's not a trivial task, and it took me a couple of years to actually understand this effect. So there are at least 13 factors which affect the science of packing. So the better the columns are packed with silica particles, the narrower your peak width is. And narrow peak width is required so that you can fit as many peaks as we like in a given time frame. So which allows us to do ultra fast separation, in other words. The biggest challenge was how to fill our modified silica particles with the columns of dimensions about 1 centimeter or 0.5 centimeter long with silica efficiently. So if your bed is not well made, your chromatography will be really poor, your peak shapes will be poor. So the process is a really dangerous experiment, that you have to make a suspension of particles, and then you have to force that suspension through a column, and once the pressure has been applied, that suspension is filtered in the column. So your whole column is filled with silica particles, modified silica particles, and the pressure that we are dealing with is around 13,000 psi, and that is equivalent to a 5,000 kg truck placed on an area of 1 inch squared. So this is the pressure we are talking about for making those 1 centimeter long columns and 0.5 centimeter long columns. The next logical question is, what is the best column geometry? Do we have to use short columns, and what should be the diameter? For that you need to study something called as the Van Demeter curves. Van Demeter curves study the superficial linear velocity versus the reduced plate heights. On the x-axis we have superficial linear velocity, which is proportional to the flow rate, and on the y-axis we have something called as the reduced plate height. I won't go into the details, but smaller the reduced plate height, the better your column is, the narrower the peak width is. So you can see here that we investigated different geometries: 0.5 centimeter long column with a diameter of 0.4546, or 0.5 centimeter long column with an internal diameter of 0.3 centimeter, and so on. And in each case you can see that the 1 centimeter long column with 0.3 centimeter ID shows the lowest reduced plate heights, hence that's the best column. That's the best column geometry. And similarly, in the case of achiral and chiral analytes, the same behavior is observed, that the reduced plate height is lowest for 1 by 0.3 centimeter ID systems. So this is the geometry which we used for further investigation for ultra-fast separations. For the proof of concept, here we show 4 baseline resolved peaks under a second, and that's a world record in liquid chromatographic speed. And you can see here that we used a 1 centimeter long column and a flow of 7.5 mL per minute, corresponding to a linear velocity of 1.7 centimeter per second. So the flow is pretty high, but your separation has been achieved within a second. It is faster than a sensor actually. So many more examples to continue. You can see nucleosides, 5 nucleosides separated under a second. You can see plant hormones, cytokinins, all baseline under a second. Plant hormones such as auxins, all baseline again. Salicylic acid and its derivatives, they are all baseline separated under a second. And this is just done on core shell silica using a really small 1 centimeter long column, which is the size of your thumb. Instead of using a long 25 commercial column, we were able to achieve ultra fast separation, and that's a world record in speed so far. Here is an example of chiral analysis, which are important for pharmaceutical industries, and this time the silica is modified with the teicoplanin molecule, and again our column dimensions are 1 centimeter long and 0.3 centimeter ID columns. So you can see oxazolidones, lorazepam, oxazepam, they're all enantiomers, 2-phenyl propanic acid, you can see that, and all these derivatized amino acids, they all can be baseline separated under a second in ultra-fast chromatography, pushing the speed limits further. So how can we separate 100 peaks in a minute? So if you use 5 centimeter columns and you have 100 analytes in your sample and you optimize everything, you can still see 100 peaks in the chromatogram. Now the question is, and which is a very natural question, is that peaks are not fully resolved. Of course, the separation space and the time window is very small and you're trying to fit 100 peaks. But here comes the mathematical approaches that you can use various signal processing techniques, which we have developed here, is that you can use something called as the even derivative sharpening method, is shown in red. And if you apply that resolution enhancing technique, you can see a large number of peaks are now baseline resolved with their area conserved. So you can do quantitation without any problem. And there is another technique called the power law related to Gaussians, and we don't have time to go into those. But you can see if we apply those power laws, we can also enhance the resolution and we can see that the peaks are baseline resolved. So the idea is for future is that you don't need to have a baseline separation, but using digital signal processing methods, you can baseline resolve those peaks and without any loss of information. So that's what we are working on and trying better and better methods to develop signal processing techniques. So we have achieved the speed goals. Chromatography can be done very fast at very high speeds. Now the goal is how to reduce toxic solvent consumption in separation problems. And I'm going to talk about supercritical fluid chromatography as a viable solution. So let's survey the prices and the toxicity of the solvents which everyone around the world is using for HPLC experiments or UHPLC experiments. Water is of course safe, but it is very expensive if it is ultra pure. And you can look at methanol, it is expensive too, but it also causes blindness if it goes into the human body. Acetonitrile is one of the most expensive solvents, and we had a crisis in 10 years ago about acetonitrile, and acetonitrile ran short in the industry, and it was a big problem for those who were doing chromatography with acetonitrile. And this health effect is liver damage. It damages your liver. Similarly, ethanol is relatively safe as long as you're not drinking it, and the price is around $180. It's expensive again because of legal issues. And hexane is a neurotoxin. It damages your brain. It's very expensive. Dichloromethane, which is used in normal phase chromatography, it's very expensive too, and it's a carcinogen. But if you come to liquid carbon dioxide, which is ultra pure, the cost is about $17 and the weight is 25 kg and is safe. So what if we just use water, ethanol, and carbon dioxide as a mobile phase? Now there is a caveat with using liquid carbon dioxide. Liquid carbon dioxide is a very poor solvent. It does not dissolve anything. So you need to bring carbon dioxide in a supercritical state, which is a far better solvent. And you need to add a small amount of organic solvent, maybe about 10% or 5% to the supercritical carbon dioxide to enhance the solubility of your analytes in the column as well. And the rest of the system is regular. I'm just quickly walking you through the instrument is that you have a liquid cylinder of carbon dioxide that has a carbon dioxide pump. It's a liquid pump. And then there is another pump which mixes the liquid solvent with the supercritical carbon dioxide, and that mixture goes to the column, and the system becomes a regular chromatograph with some instrumental modifications, but it's very much doable. And here I show again that using very short columns which are 5 centimeter long or 2 centimeter long, you can do ultra fast chiral separations using very green solvents. So oxazolidones, here I'm showing an example that using 5 centimeter column and 2 centimeter columns, you can do the separation with less than 20 seconds. How should we make supercritical fluid chromatography even greener? So instead of using methanol with supercritical carbon dioxide, what we came up with is that why don't we use azeotropic ethanol? So azeotropic ethanol is really easy to manufacture. It is dirt cheap and it comes from the fermentation of cornstarch, and corn industry is really big in the US. So you can isolate starch from corns and convert that into ethanol, and you simply distill it. Now the thing is that why pure ethanol is very expensive is because you have to remove water from it. But azeotropic ethanol distills as such with a composition of about 95% ethanol and about 4% water, and that's constant. And it is available at very low prices everywhere. Here we clearly demonstrate the concept we just discussed earlier, is that why don't we use supercritical carbon dioxide with the azeotropic ethanol which is obtained from corn rather than from any chemical synthesis or liver damaging solvents. So if you use absolute ethanol, which is very expensive due to legal reasons because you require licenses and so on, you can see that if you want to analyze 4 chiral molecules with their enantiomers, you have to wait for 14 minutes, and yet not all enantiomers are resolved. Let's switch to methanol, which is toxic and expensive both. Still you do not see full baseline resolution, there is coelution problems, and the peak shape is not that great. You still have to wait for 10 minutes. If you switch to azeotropic ethanol, which is also known as 190 proof ethanol in the industry, you can see that you have all 8 peaks, which is expected from the enantiomers. So each molecule had one enantiomer here, and they are very high resolution and they are all baseline resolved. So this is economical and this is safe. So why don't we switch to carbon dioxide solvents plus azeotropic ethanols for future applications? SFC is not very common in Pakistan as such and in other places because the instrumentation is slightly more complicated, but it is worth investing in this area as well. So finally, the conclusion, the future outlook. Ultra-fast and sub-second separations in chiral liquid chromatography were demonstrated for the first time, but I'll tell you that the current, even the latest UHPL instruments are not ready for such high-speed separations, and we had to modify the instrument and do a lot of software processing as well. And in future, with the rising cost of solvents and stricter environmental rules, we'll have to look for greener solvents, and the most common abundant solvent is carbon dioxide and water, and ethanol also comes from natural resources. Therefore, high speed separations with sub or supercritical carbon dioxide are really promising. So I hope in Pakistan we'll adapt SFC in analytical procedures as well. With that, thank you very much for attending the talk, and if you have any questions, feel free to discuss or email me, and I'll be happy to answer that. Thank you very much for listening.